Black holes are attractive. That's funny, Mr. Dewick. Let's talk about, first of all, asteroid impacts. Suppose a 45,000 kilogram asteroid is traveling at 4.67 times 10 to the 4th meters per second at a distance of 1.2 times 10 to the 7th meters from the center of the Earth. A says, how much kinetic energy would it have if it impacted the Earth? What approach do you think I'm going to use to solve this? Am I going to say gravity is what's pulling me in a circle? How do I know we're not in a stable orbit? Don't see the word orbit anywhere. Am I going to start out by going work equals change in potential plus change in kinetic? No. How do I know? This question does not ask for or mention work. So what's the third option that we've resorted to? Is there a change in height? Is there a change in speed? It mentions kinetic energy. I'm going to use conservation of energy. By the way, I like this question, I like this question, I like this question, but I also don't. I would never ask you part A. What I would ask you is part B. I would just say, how fast will it hit the ground at? And I would expect you to realize this is a job for conservation of energy. Are any of these zero? Kinetic energy is zero if we're starting at rest. Are we starting at rest? Potential energy is zero, not on the Earth's surface, because we're cosmic. It would be zero if we started all the way out at infinity. Did we start all the way out? Nothing's zero? Okay, well, before I start writing out all the formulae, I think they want me to find KE final. I think the very first thing I would say is, I guess KE final is going to be KE initial plus PE initial minus PE final. I would get the KE final by itself. And this, Garrett, is also, if they had asked me to find the impact speed, what I would do first. I would say, I know it's hidden in there, let's get that by itself first. Then I would, okay, substitute my equations in. It's going to be a half little m V final squared equals a half little m V initial squared plus negative big G big M little m over R initial minus negative big G big M little m over R final. I got a minus in the middle there, which is a plus. Oh, will the mass of the asteroid affect its speed? No. It will affect how much. Wait a minute. This is asking us to find the kinetic energy. So I guess I'm not going to cancel out the m's yet. It wants me to find the kinetic energy. If I was being asked to find the speed, I would probably cancel out the little m's. But for now, in fact, I probably could have just left this as KE final. That's what they wanted. It's going to be 0.5 times, glad you made it, sir, 45,000 times the initial speed, 5.67 times 10 to the 4th. Don't forget the squared. Take away big G, mass of the Earth, 5.98 times 10 to the 24th. I'm not even going to be able to fit this on one line. Mass of the satellite, 45,000. All over. What's my initial radius? Do I need to add the radius of the Earth to that? It says, okay, this is important because this is a common mistake. Some people always want to add the radius of the Earth. No, this one they gave me from the center of the Earth. If it had said altitude, I would have to add the 6.38 times 10 to the whatever it is. So I can go straight to 1.2 times 10 to the 7th. And then it's going to be plus same thing times same thing times same thing divided by, and I guess the final one is the radius of the Earth, 6.38 times 10 to the 6th. Zach, I don't think I would try typing this whole thing in one line. I think I would do each expression to about 5 sig figs. So it's going to end up being, for the first one, how much kinetic energy initial does it have? 0.5 times 45,000 times 5.67 times 10 to the 4th squared. Wow. 7.2335, 7.2335, 7.2335 times 10 to the 13th. Is that correct? Everybody else got that too or not? Yep. And then I'm going to have takeaway 6.67 times 10 to the negative 11. Oh, typo. Times 5.98 times 10 to the 24th times 45,000 divided by 1.2 times 10 to the 7th. Sorry, Aiden, I'm covering up what you're trying to get. Minus 1.4957. Is that correct? Everybody else got that too? And then plus, at least I can backspace and edit this, 6.38 times 10 to the 6th. 2.8133 times 10 to the 12th. All right, how much kinetic energy does it have? .2335 scientific notation 13 minus 1.4957 scientific notation 12 plus answer button, at least I can use that. And I get, I'm going to write 7.37 here. I would probably take 7.36 or 7.37 because of the 5 after the 6. We've done a whole bunch of sig figs and rounding, and this is not using our answer button all the way through. So I'm going to go 7.37 times 10 to the 13th joules. Is that a lot? Well, I did some research to try and put this into perspective, and so the atom bomb that exploded over Hiroshima had 6.3 times 10 to the 13th joules. Basically, this would be like a small atom bomb. So, is that a lot? It's a fair bit! 45,000 pounds. Is that a big asteroid? Not really. These are made out of rock. Not really. Oh, how fast would it be traveling on impact? Now, I'll start out with kinetic energy equaling a half mv squared, and I'll get the v by itself. This is probably how I would do this whole question, Mason, if they just asked me to find speed. Although I might have canceled out the little m on this line right here to make my work a bit easier. But what I would not have done is actually get the v by itself. I would have turned the whole right side into a number, then I would have got the v by itself. Or if they had asked me to find the initial radius, how far it had started from the Earth, if they had told me how hard it hit, same thing. I would have got PE initial by itself. I would have gotten an entire answer. Only then would I've got the R by itself. But here, I guess it's going to be 2 times the kinetic energy divided by the mass, square root. 2 times answer button divided by 45,000, square root of that. And I get 57,214 meters per second. 57 kilometers per second. Is that fast? Pretty fast. More than escape velocity. I think escape velocity was 11,000 something meters per second. Do asteroids hit us? Have asteroids hit us in the past? Yes. Will they hit us in the future? Yeah, there's a football stadium-sized one that's going to hit us in 2036. You guys haven't heard about the football stadium-sized one that's going to hit us? You don't read? Put your pencils down, look up. You guys got to read science news. Pardon me? No, it'll wipe out the entire West Coast. Please, wipe out a city. Go big or go home. City. So, let's tell you about Apophis.
So have they figured out how to stop it then?
Oh, patience, grasshopper.
Yes, in the middle. Just speak up and you won't need the microphone.
Foundation, you spoke about an asteroid coming towards Earth.
She didn't forget that asteroid, did she? She didn't forget the asteroid. So you want a quick update on the asteroid. There's an asteroid. The size of the Rose Bowl.
Football stadium.
Headed towards Earth. It's called Apophis, named for the Egyptian god of death and darkness. Now, it wasn't coincidental that it was named that. When this asteroid was discovered in December 2004, its trajectory was calculated based on a short segment of its orbit, because you look from one day to the next, it's in a new place in the sky. These folks are moving. Once you saw that its trajectory would intersect the orbit of Earth, you don't name that asteroid Bambi or Tiffany, right? You're going to give it a name befitting its...
Some sense of gravity.
Yes. That pun was surely intended. The reason why you never heard of it, perhaps, is because it was discovered that this aspect of its orbit was calculated and reported on the same week of the Indonesian tsunami.
So you might recall Boxing Day 2004, there was a tsunami. You were young, but it killed 250,000 people. Well, that dominated the headlines. Entire people tribes were wiped out. Entire islands of people were scoured clean and nobody there anymore. Okay, there was a massive earthquake and a massive tsunami in Indonesia. So obviously that dominated the news.
Okay, I think it was end of 04 or 05. I forgot which of the 2 years it is. Same week. Odd thing is, of course, 200,000 people died in that tsunami. Odd thing is, if this asteroid hits in a place where it could hit, and I'll describe that in a minute, it will hit in the Pacific Ocean. It would create a tsunami in the Pacific Ocean that would make the Indonesian tsunami look like a street puddle that's slightly over-spilled its edges. So I think rightly immediate attention was given unto the Indonesian tsunami, but that was not an excuse to then never have the press talk about this object. It's a real object. And there's something called the keyhole. It'll have a close approach to Earth in the year 2029.
How old will you all be in 2029? Do the math. Okay? It'll make the news, it'll be headline news that year.
In April 13th, which, by the way, is a Friday. It will come close enough to Earth to dip below our orbiting communication satellites. For that passage, that will be the closest, largest thing we have ever observed in the history of our observing the universe. That's a shot across our bow. The uncertainty in its orbit at this moment is such that for that passage, there is a range of orbits it could have, which, if it goes through what we're calling the keyhole, Earth's gravity on it will be just right. Or rather, just wrong. Just wrong. That the next time around, it will hit Earth. 7 years later, April 13th. If it goes to the center of the keyhole, it'll hit the Pacific Ocean 500 kilometers due west of Santa Monica. It'll plunge into the Pacific Ocean to a depth of 3 miles. At that depth, it will explode, cavitating the ocean with a hole 3 miles wide, 3 miles deep. That impulse will send a tsunami wave that will basically wipe out the entire west coast of the United States and the east coast of Asia.
City. Do better than that.
Now, oceans don't like having big holes in them. So this 3 mile high wall of water does what? It's a hole in the water. What does it do? Falls back in the hole. This is not Moses here. We're talking. It won't just stay there, like in the movie. It'll fall back into the hole, slosh into itself, rise high into the air, fall back to the ocean, cavitate the ocean again. And it'll do this with such ferocity, it'll repeat itself about 50 times, taking about an hour. So every time it cavitates the ocean, it sends another tsunami. So it's not will be just one wave like the Indonesian tsunami was. This will be 40 waves, 50 waves. Now, each wave has to pull back out to get ready for the next one. And it's separated by about a minute. So there's a limit to how far these waves will get on shore. We think it's about a quarter of a mile. If you're more than a quarter mile inland, you can just watch this happen. If you're not, now, the $1 million Malibu homes, they will feel this first tsunami wave. The tsunami will basically pick up the homes. It'll bring them back out to sea. Then the next wave will come and return the home to the shoreline. But now the home is in a slightly different shape. And as this continues, all man-made objects along the coastline and trees and debris basically becomes this churning, ablative mass, wiping clean the entire coastline. Now, nobody has to die, because we'll know this well in advance. But I found there are two people who will die. There is the stupid surfer who says, I got to do that tsunami wave, dude. You know they're going to be out there. Okay? So we'll have dead surfers and dead weathermen. You've seen them. There's the camera guy over there. Come closer. Watch the hurricane smash into the... Get this shot. Can you see this? I'm reporting from the hurricane. Now, I'm a scientist. If this asteroid goes through the keyhole, there'll be people evacuating the West Coast, building shelters, stockpiling food. There'll be people praying to their gods. There'll be people doing all kinds of things. I'd rather be doing something about it. This is where engineers come in, and physical scientists, and physicists and astrophysicists. So, we've got top people right now working on a way to deflect the asteroid. Therein is the power of science. You don't have to build a shelter from something that could kill you. You can prevent the thing from killing you in the first place. It's like, how do you solve acid rain? Well, let's have acid rain-proof umbrellas. No. You want to stop the rain, all right? How is your brain wired for finding solutions? So, there you have it. So we'll monitor the news at that time. By the way, it is not known who will pay for that deflection mission if it comes to pass. Probably America, but asteroids can hit anywhere in the world. And the UN, well, there's a space unit of the UN, there's no funding stream. Suppose this were headed for Indonesia. Would we pay for that to deflect it? Suppose we pay to deflect it, and we only half deflect it, then it hits somewhere else. That's an interesting geopolitical problem. So it's not just fix it and go home. It's more complex than that. Oh, by the way, you got these guys who like stockpile nukes, and that community wanted to blow the sucker out of the sky. There's that. The folks who want to use the nukes that we have. And the problem is, here in America, we're really good at blowing stuff up. We're less good at knowing where the pieces go after the explosion. Whereas when you deflect something, you can monitor your progress all along. But another question?
So that is Apophis. Now that video is from about 2014. Since then, we've had much better data, because obviously we've been watching it. The likelihood, it will come by in 2029. The likelihood of it going through the keyhole in the wrong manner is near zero. So will it hit us in 2036? Almost, I'm going to say no. It's not zero, but it's close enough to zero. I'm not losing any sleep over that one. But there's nothing that makes us special. So as you become voting adults, among many other problems that we're handing to you, we've botched the environment, we've botched the economy, you're going to have to deal with some social challenges. But I'm also going to say to you, be aware of the universe out there. We may have to deal with that too. So vote with your tax dollars. But don't lose any sleep over Apophis. It'll be some other asteroid that wipes us out. Oh, that. Anyway. Geosynchronous satellites maintain their orbit over the same place on the Earth at all times, somewhere over the equator. What would the period be of such a satellite? It would be the period of the Earth, which is... Yeah, and we talked about, I showed you a video a while ago where we realized actually it's technically not 24 hours. It's 24 hours if you're noticing when the sun, the average of when the sun returns to its location. But the Earth itself has a period of, is it 86,100? Seconds, 8.61 times 10 to the fourth. Okay. So this, by the way, is really, really useful. Most of our communication satellites are geosynchronous. Why? Because they stay in the same location relative to the Earth. So you can point the satellite dish at that communication satellite, and you don't have to adjust that satellite dish. It's going to stay there. What would the radius of such a satellite be? Well, we're in orbit. So, gravity is what's pulling me in a circle. If they ask me to find a radius or a period or an orbital speed, I start here. Or an orbital altitude, I start here. So it's going to be big G, big M, little m over r squared equals m. Which version of AC am I going to use? Oh, the one with the period in it. So 4 pi squared r over t squared. Will the mass of the satellite change its orbital radius? Nope. Does an r cancel here? I got an r squared on the left and an r on the right. Does an r cancel? No, they're not on the same level. In fact, if stuff moves diagonally, that'll give me an r cubed there. That'll give me a t squared there. And this will give me a 4 pi squared. I'll end up with r cubed equals big G, big M, t squared over 4 pi squared. Ah, how do I get rid of a cubed? I get to use my cube root button again? Oh boy. Okay. Let's see if we can go straight to the answer without writing out the numbers. It's going to be big G, 6.67 times 10 to the negative 11. Mass of the Earth, which I think is 5.98 times 10 to the 24th, times 86,100 squared, divided by bracket 4 pi squared. And then I got to go hunting for my cube root button, which on my calculator is there. Is that right? That looks wrong to me. Maybe it's right. Is it right? Do you get 4 to the same thing? Okay. 4.22 times 10 to the 1, 2, 3, 4, 5, 6, 7. Okay. 4.22 times 10 to the 7th meters. It's a ways out there, but we do this all the time because it's just so handy to have a satellite that stays motionless relative to the Earth. And that circumference at that high around the equator, it's a big enough circumference that even though we've got thousands of satellites there, it's not getting very crowded. Turn the page. Let's talk about black holes. I like example 3. I like example 3. Example 3 is a nice question. Suppose an 18,000 kilogram spaceship is orbiting a black hole at an orbital radius of 8.8 times 10 to the 9th meters. The black hole has a mass of 6.8 times 10 to the 32 kilograms. All right. Sarah, what does A want me to find? Oh, that's easy. That's this, right? Field starts with an F. Big G, big M, little m over r squared. No, that's not. What's that? Not gravitational field, but gravitational force. What's our symbol for gravitational field? Little g. Ah, on my formula sheet, I noticed Mr. Dewick gave me this. Little g is Fg over M. Well, of course it is, because from Physics 11, it's the obvious one. Get the little g by itself. Oh, but we're cosmic. So, Sarah, I guess it's going to be big G, big M, little m over r squared divided by little m. I guess gravitational field strength is big G, big M over r squared. Okay, so it's going to be big G, M is 6.8 times 10 to the 32. R is 8.8 times 10 to the 9th. I double checked. They did say radius and not altitude. Don't forget the squared. What do you get for the gravitational field strength? Probably bigger than 9.8 because, you know, black hole. What do you get? George, what'd you get? Sorry? So 586? Anybody else? Yeah? Units. Is that right? Is it 586? Units. You can either say meters per second squared, or, since it's force divided by mass, I'm going to use newtons per kilogram. But I'd take meters per second squared. Would this be fatal to those on board the spaceship? Why or why not? So would this be fatal to those on board the spaceship? It depends. What's Earth's gravitational field? You all know this. 9.8. What is it on the ISS? What 9.1, 9.2? Do the astronauts feel it on the ISS, though? Why not? Because they're in orbit. Are we in orbit? In this question, are we in orbit? While they're in orbit, they won't feel it. They'll be okay. Getting there, though, and leaving there, that I don't have a way to do without probably killing them yet. That's why I wrote depends. At this moment, actually, if you could somehow Star Trek technology beam yourself into that spaceship, you'd be in free fall. No normal force, no gravitational, in a gravitational field, but you wouldn't notice it. But leaving it by actually flying the spaceship out or flying the spaceship in, yeah, that would probably be fatal. Ooh! What's the escape velocity required to leave the black hole's gravity well? Huh. How do we solve for escape velocity? What was our approach? Now, you may have memorized the equation, and if you have, fine. But it was conservation of energy. But it was weird. We said you were going to start off by firing your engines, so you'd have kinetic energy. You aren't out at the edge of the universe, so you have potential energy. But you would like to come to a stop, and you would like to have be out at the edge of the universe, so you'd like to have no potential energy. It was this weird setup page where it equaled 0. Oh, but that actually worked okay, because when we went a half m v initial squared plus negative big G big M little m over r initial equals 0, we just plus that over. We ended up with a half little m v initial squared equals positive big G big M little m over r initial. We noticed an m canceled, and then you pointed out times by 2 square root. So here's escape velocity. It's the square root of 2 big G big M over r. You know what? If I go back, no, I was, oh, you guys might. If you have your G value, you might still have big G big M over r squared on your calculator. Delete the squared times by 2 square root. What's the escape? I know Earth's is 11,000 something. This is going to be bigger, I suspect, because the gravitational field strength is stronger. It's probably going to be pretty big. Yeah? 3.2. So 3.2 what times 10 to the what? 3.21 times 10 to the 6th. Is that right, folks? Let's suppose that Mudd was an astronaut on this mission, and he's working on the outside of the spacecraft doing a spacewalk. But he wasn't careful with his tether. He goes to click his tether in, and he doesn't realize it didn't quite catch. And so as he's absent-mindedly working, suddenly, he's drifting away from the spacecraft and slowly drifting towards the black hole. What would it be like to fall into the black hole? Spoiler alert, you're going to die. But along the way, what would happen? Well, as you got closer and closer, you would be accelerating, but the gravitational field strength would be increasing, and it would be increasing so rapidly that you would notice there was actually a difference between the gravity on your feet and the gravity on your head. Let's say you're going to fall feet first like you're cliff jumping. And so you would actually feel a tug on your feet stronger than on your head. And at first it would feel pretty good. Like when you get up in the morning and first thing you like to do is you stretch. It would feel not bad. But as you continued to fall, that difference in pull would get stronger and stronger, and now it would resemble a medieval torturer's rack, and it would get stronger and stronger. In fact, eventually it would be so strong it would overcome the molecular bonds holding you together, and you would bifurcate, probably somewhere around your belly button. and now your problems are kind of over in that you're not aware of what's going on. But then each piece of you would bifurcate as you fell further and further. But not only that, the black hole's gravity well is so strong, it's warping space-time. You would actually be compressed from the side. You would be slowly being converted into this stream of molecules that was being funneled down through this smaller and smaller pipe, almost like toothpaste being extruded from a tube. And eventually, all of the molecules that were once you would end up spiraling down into the black hole. We have a name for that. Does anybody know the name we've given to this process of being bifurcated and squeezed simultaneously by a black hole? It's spaghettification, yes. Spaghettification. So when your parents ask you what you learned today, Mummy, 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 we're not going to die in 2036, but 2029 will be a little interesting. And we learned spaghettification. Yes? Asteroids are terribly non-reflective. You got to realize anything that we see, either it's giving off its own light, those are stars. Anything else that we see, it has to be the sunlight or the moonlight reflecting off of it. And asteroids are very, very jagged, so you're not getting a whole bunch of light bouncing right back to you. And they're pretty dusty. It's like shining a flashlight on charcoal. You don't go, wow, that's blinding me from the reflection. So probably not with the naked eye, but maybe, depending on what its makeup is. Example 4 is a repeat of example 3 for A and for B. But I'd like to jump to part C, please. What radius from the center of the black hole does the event horizon begin? What is the event horizon? Do you remember? We talked about this the other day. So how does a black hole work? You know what? We need to dive into this. Put your pencils down. Look up. You might recall a few years ago, scientists released the first ever image of a black hole. We had finally imaged one, and this was the image right here. Remember seeing that a few years ago? What are you seeing? What you're seeing is actually way cooler than you realize. Come on. Really going to make me remember? Let's try doing that, Mr. Doug. Well, so one of my favorite YouTube channels is this channel, Veritasium. Derek released this video the day before the black hole image was actually released. He tried to predict what we might see. So remember the image that I showed you, which was this one here? Okay, let's see how close he was.
On Wednesday, April 10th, 2019, you will probably see the first ever image of a black hole. That's when the Event Horizon Telescope will be releasing their results. And I haven't seen them yet, but I think they're going to look something like this. And I can be relatively confident because, well, it's going to look a bit like a fuzzy coffee mug stain. But if you are disappointed by this image, I think that misses the gravity of the situation. From this image, we should be able to tell whether the general theory of relativity accurately predicts what happens in the strong gravity regime, that is, what happens around a black hole. What I want to do here is understand what exactly we are seeing in this image. So here is my mock black hole of science. And this sphere represents the event horizon. That is the location from which not even light fired radially away from the black hole could be detected by an outside observer. All of the world lines end up in the center of the black hole in the singularity. Once you're inside here, there's no coming back, not even for light. The radius of the event horizon is known as the Schwarzschild radius. Now, if we were just to look at a black hole with nothing around it, we would not be able to make an image like this because, well, it would just absorb all electromagnetic radiation that falls on it. But the black hole that they're looking at, specifically the one in the center of our Milky Way galaxy, Sagittarius A star, has matter around it in an accretion disk. In this accretion disk, there is dust and gas swirling around here very chaotically. It's incredibly hot. We're talking millions of degrees, and it's going really fast, a significant fraction of the speed of light. And it's this matter that the black hole feeds off and gets bigger and bigger over time. But you'll notice that the accretion disk does not extend all the way into the event horizon.
So the first thing to realize is, oh, wrong button, Mr. Duke. That black area, that's not the black hole. The black hole is probably significantly smaller. Why?
Why is that? Well, that's because there is an innermost stable circular orbit. And for matter around a non-spinning black hole, that orbit is at 3 Schwarzschild radii. Now, in all likelihood, the black hole at the center of our galaxy will be spinning, but for simplicity, I'm just considering the non-spinning case. You can see my video on spinning black holes if you want to find out more about that. So this is the innermost orbit for matter going around the black hole. If it goes inside this orbit, it very quickly goes into the center of the black hole, and we never hear from it again. But there is something that can orbit closer to the black hole, and that is light. Because light has no mass, it can actually orbit at 1.5 Schwarzschild radii. Now here I'm representing it with a ring, but really this could be in any orientation, so it's a sphere.
It would be a sphere, right? Three-dimensional.
Sphere of photon orbits. And if you were standing there, of course you could never go there, but if you could look forward and actually see the back of your head.
Because the light from the back of your head would have orbited and come all the way around and hit your eyes. So there'd be some very strange optical effects there.
Because the photons could go around and complete that orbit. Now, the photon sphere is an unstable orbit, meaning eventually either the photons have to spiral into the singularity or spiral out and head off to infinity. Now, the question I want to answer is, what does this black, quote-unquote, shadow in the image correspond to in this picture of what's actually going on around the black hole? Is it the event horizon? Are we simply looking at this? Or is it the photon sphere or the innermost stable circular orbit? Well, things are complicated. And the reason is this black hole warps space-time around it, which changes the path of light rays. So they don't just go in straight lines like we normally imagine that they do. I mean, they are going in straight lines, but space-time's curved, so yeah, they go in curves. So the best way to think of this is maybe to imagine parallel light rays coming in from the observer and striking this geometry here. Of course, if the parallel light rays cross the event horizon, we'll never see them again, so they're gone. That will definitely be a dark region. But if a light ray comes in just above the event horizon, it too will get bent and end up crossing the event horizon. It ends up in the black hole. Even a light ray coming in the same distance away as the photon sphere will end up getting warped into the black hole and curving across the event horizon. So in order for you to get a parallel ray which does not end up in the black hole, you actually have to go out 2.6 radii away. If a light ray comes in 2.6 Schwarzschild radii away, it will just graze the photon sphere at its closest approach, and then it will go off to infinity. And so the resulting shadow that we get looks like this. It is 2.6 times bigger than the event horizon. You say, what are we really looking at here? What is this shadow? Well, in the center of it is the event horizon. It maps pretty cleanly onto the center of this shadow. But if you think about it, light rays going above or below also end up crossing the event horizon just on the back side. So in fact, what we get is the whole back side of the event horizon mapped onto a ring on this shadow.
In other words, if you could see this, you would see the black hole, but also in a ring around it, you would see the back of the black hole because light is being warped that dramatically. When it gets weirder, but cooler.
So looking from our one point in space at the black hole, we actually get to see the entirety of the black hole's event horizon. I mean, maybe it's silly to talk about seeing it because it's completely black. But that really is where the points would map to on this shadow. It gets weirder than that. Because the light can come in and go around the back and, say, get absorbed in the front, you get another image of the entire horizon next to that, and another annular ring, and then another one after that, and another one after that, and you get basically infinite images of the event horizon as you approach the edge of this shadow. So what is the first light that we can see? It is those light rays that come in at just such an angle that they graze the photon sphere and then end up at our telescopes. And they produce a shadow which is 2.6 times the size of the event horizon. So this is roughly what we'd see if we happen to be looking perpendicular to the accretion disk. But more likely, we will be looking at some sort of random angle to the accretion disk. We may be even looking edge on. And in that case, do we see this shadow of the black hole? You might think that we wouldn't. But the truth is, because of the way the black hole warps space-time and bends light rays, we actually see the back of the accretion disk. The way it works is light rays coming off the accretion disk bend over the top and end up coming to our telescopes. So what we end up seeing is something that looks like that.
This is not the top of the black hole. This is the back of the accretion disk behind the black hole facing away from us. But the light got bent and warped so strongly that it ended up getting bent towards our telescope.
Similarly, light from the bottom of the accretion disk comes underneath, gets bent underneath the black hole, and comes towards us like that. And this is where we get an image that looks something like the interstellar black hole. It gets even crazier than this, because light that comes off the top of the accretion disk here can go around the back of the black hole, graze the photon sphere, and come out the bottom right here, producing a very thin ring underneath the shadow. Similarly, light from underneath the accretion disk in the front can go underneath and around the back and come out over the top, which is why we see this ring of light here. This is what we could see if we were very close to the black hole, something that looks truly spectacular. One other really important effect to consider is that the matter in this accretion disk is going very fast, close to the speed of light. And so if it's coming towards us, it's going to look much brighter than if it's going away. That's called relativistic beaming or Doppler beaming. And so one side of this accretion disk is going to look much brighter than the other. And that
one side is going to look brighter than the other. Yes.
That's why we're going to see a bright spot in our image. So hopefully this gives you an idea of what we're really looking at when we look at an image of a black hole. If you have any questions about any of this, please leave them in the comments below, and I will likely be making a video for the launch of the first ever image of a black hole. So I'll try to answer them then.
So that image has a lot more depth to it than you realize. By the way, just to put things in perspective, there's the Sun in the middle, there's Pluto, there's Voyager 1. This is the size of the image of that black hole that we got in 2019. Yeah, it's pretty impressive. Black holes can get pretty large.
How do we know that we get identification if we actually see it?
Math.
Couldn't our math be wrong?
Unlikely. General relativity, every bizarre prediction that it's made, as soon as we've developed the technology to run the experiment, look at that! He was right after all. Gravitational waves just a few years ago, photos of black holes, all, experimentally, it just keeps reconfirming general relativity. We do know there's a fundamental flaw between general relativity and quantum physics, because if you try and start with general relativity and shrink it down to the really small subatomic, you get nonsense. If you try and start with quantum physics and make it go really big, you get nonsense. So we know somewhere there's got to be a flaw. So we're looking for what we call the theory of everything, TOE, or the grand unification theory, the ring of power version of one theory to bring them all into one theory. But also we know that dark matter and dark energy, which we don't have good explanations for, make up 95% of the universe. So we're cognizant we've only observed about 5% of the universe. Speaking of black holes, by Einstein's general relativity equations. Basically, you're dividing by zero, taking the limit. And at first, scientists were skeptical, but we now know there are many black holes out there. So the real question, Zach, is how big are they? Anything can become a black hole if you can crush it down beyond the Schwarzschild radius. So if you crush the sun to the size of a small town, that would be dense enough that at that location the gravitational field escape velocity would require you to go faster than light. Crush the Earth, about the size of a peanut. There's a black hole about the size of Manhattan. But now, let's go big. Black hole is the size of Mars. How much mass does it contain? About 1,000 suns worth. Here's a mid-range black hole. Let's go bigger. billion suns worth. These are supermassive. Most galaxies have a black hole at their center. That's what most galaxies are spiraling around. Our own galaxy has a black hole about 4 million suns worth. This is called Sagittarius A star. Or Sagittarius A. holes are pretty cool. I'm going to pause there because you have a take-home quiz to do.